Okay, welcome to day 2 notes, pre-calculus. We're talking about chapter notes on 6.1 here. This is what we talked about yesterday. So you have different types of triangles that could be formed with an angle given in two sides. And oftentimes they don't specify which sides we're covering and what angle we're covering. So we have to look and see if indeed the angle you're given and the two sides can actually form a triangle. So we can do this in a couple different ways. We can look at A and B, the angles or the sides given, and we can take a look at this chart and find out which one that fits. Now, there is a couple cases where you actually have to find the H here, and then you're going to form different types of triangles as well, such as this one right here, which I'll talk about here in a second. That one is going to form 2. This one here would form none. Okay, and then this one would be a right triangle because A and H are going to be equal to each other. Okay, so let's take a look at an example here. I'm going to be flipping back and forth between these notes here and then this one here. All right. So what I did is we have A is 12 and B is 31. The angle doesn't throw me off a whole lot. It's 20.5, so that probably means that this can fit into a triangle. We just got to figure out which one. So since A is less than B, if I go to my chart here, I check out this chart and I see that A is less than B right here. Okay, well that would mean this is none. Okay, that really is our only option if we just have A and B, because A is not bigger than B, which would fit this one here, but it's not. All right. So the only one it could possibly fit that could form some triangles would be this one. Okay, so and that would be 2 triangles. All right, so I'm going to go ahead, I'm going to take a look at this. I'm going to go back, all right. H is equal to B times sine angle A, all right. And if I figure that out, that would be 10.86. Okay, so what it would fit then would be this one here. Okay, and that means that it would be 2 triangles. Okay, so here's what we're going to have to look for. Now, you're going to have to form one triangle, which is acute, and you're going to have to form one that's obtuse. I'm going to do my best to draw this, but I also included a picture in case you don't like my drawings. But these ones actually already solved out for you. Okay, so you can see the angle affected is going to be angle B. Okay, so different types of triangle. Okay, there's one of them, and then this one would be, again, I apologize for my drawings, but this is what, well, let's try this one more time. Go here, like this. Okay, so this one here is B1, B2. Okay, so this is our angle A. It's going to be the same on both of these, and then this one here would be your C. Okay, so across from this, let's just see what we have. Okay, we have angle A, that's 20.5. All right, we have we have side B, which is 31. Now that's going to be the same here as it is right here. Okay, and we also have angle A, side A. Okay, so that is what we have so far. So we're going to figure these out individually. All right. Okay, so now one of these is going to give an acute angle, and then the other one, you're going to have to subtract whatever that angle is for B off of 180 degrees. And that's how you find out what your other angle is that you could possibly have with the second triangle. Okay, so let's go ahead. Let's use the law of sines to figure this out. I'm going to go ahead and, again, find out angle B right away. Okay, so once I do that, I can figure out what angle C would be in each one of these. Okay, so I have sine. I'll go ahead and put the sines on top here. We have sine 20.5. That is over 12. Okay, and then we have angle, or sine of B over 31. All right. Okay, and then we just have to figure this out. So if I cross multiply, and a lot of times you could probably just do this in your head, but if I cross multiply, sine of 20.5, and that's times sine of 31, and then divide it by 12, Okay, so I'm going to get a pretty small decimal, and remember the way you have to figure this out is you have to put sine, whatever the answer is, okay, and then you should be able to find your side length, or excuse me, your angle for B. Okay, so if I do that, and I'm going to leave the decimals as is in my calculator, so I'm going to go second sine, second answer, okay, and I get 64 point. We'll go 78. Okay, so this one here is 64.78 degrees. Okay. Now, if you want to figure out the one to the right, you would have to take 180, and this works every single time, minus 64.78. So it's almost as if we can swing our leg open and closed, and at two different points, we form two different triangles with these two different angles. Okay, so that's how that works. It's swing door theorem, which you learned all the way back when you guys were sophomores. Okay, so 115.22 degrees. Okay, so now that allows me on both of these to find out what the C is. Okay, so angle C, not side C. But now I can figure out the angle is on the left side, and then I can figure out what it is on the right side triangle. Okay, so if I go ahead and I figure out the left side one, I'm just going to subtract these two off quick. Okay, so we have 180 minus 20.5 plus 64.78. All right, so I get 94.72. So this would actually be an obtuse triangle as well. And then if I do it on the right side, I get 20.5 plus 115.22. All right. I'm going to take 180 minus my second answer again. Looks like I would get 44. So 44.28 degrees. Okay. So, and then finally, if you want to find out what side C is, we can do that. All right. So I'm going to extend my page here. I'm going to go ahead and set this up. So I usually take the sure one, which was angle A and sine A. So I'm going to go sine 20.5 over 12. And then that's equal to our sine C, which happens to be on the left side, 94.72. And then that's over C. All right. So if I cross multiply that, I should be able to figure this out without any inverses or anything like that. So I have sine of 20.5 times, should be 12 times sine of 94.72. We would divide that by sine of 20.5. Okay, so we get 34.15. Now that checks out if you take a look at it, because 94.72 degrees, you better have the biggest side length across from the biggest angle on the left side. Okay, so that one is done. The only thing that we have to change now would be we set the A's up the same. We also have your C now, so in this one, instead of 94.72, we would have 44.28. All right, so basically the same thing we just did, except for now we're changing the angle for C. Okay, so if I go ahead and multiply this out, I would get 12 times sine 44.28. Okay, and I would want to divide that by sine 20.5. Okay, so I get 23.9. We'll go with 92. All right, so that would be our the angle given. Okay, so it looks like that one would check out as well. Okay, so across from 44.28, that should be the second biggest side, and it is, so that's a good thing. So, and then across from 20.5 is 12, and then E provided us with our biggest side length on the one on the right side here. Okay, so that is how you have two different triangles. I would focus on making sure that B is the angle that we change. That makes life pretty easy. I'll give you a better picture here. All right, so there you go on this one. They didn't figure out the other stuff like we did, but this is what they came up with. So a much more accurate drawing than mine, but do your best on the drawings, and I won't hold it against you if you do something kind of funky. Okay, so let's go to our last concept that we want to talk about. So this is an area of an oblique triangle. So in other words, if you don't have a right triangle, how do you figure out the area? There's a couple different ways to do this, but one of them is this method here. Okay, so basically what it is if you have an angle, but you don't have the side length across from that angle given. Okay, you can use this formula here. All right, so notice how, say on this one here, we have the angle A, but we don't have what's across from that. So, but we do have B and C. So if you're given two side lengths and an angle, and even if they don't specify it, you should be able to use this formula for your area. Okay, so let's take a look at this example here. It says find the area of a triangle lot having two side lengths of 90 and 52 meters and an included angle of 102. So notice how they don't specify if the angle is across from these two sides. So we're going to assume that this is an oblique triangle. Okay, so, and then of course it would be an obtuse triangle. So if you want to get more technical on that, it would fit this side over here rather than the side or the triangle on the left. Okay, so let's go ahead and figure it out. So it's area equals 1/2. You have your two side lengths, so 90, 52, and then the sine of 102 degrees. Now, you may remember from the past where we had to find these in radians. Okay, you don't have to do that with this formula here. Okay, so I would probably just go ahead and plug this into my calculator. You could simplify the 90 or even the 52, so let's just do that quick. So I'm going to take 45 times 52 times the sine of 102. Okay, so we get 2,288, and then we'll go to the hundredths again, so we'll go 0.87. And let's see, that was meters squared. Okay, so pretty simple formula if you can just set it up correctly. All right, let's go to our next example. Okay, so this one here, this also brings back a method from the past as we go through this, and you'll see that. It says the course of the boat race starts at point A in figure 6.9 and proceeds in a direction south 52 degrees west to point B. Okay, then the direction is south 40 degrees east to point C. Okay, and then finally back to A. So in other words, the boat went in a race along the triangle. Okay, so this one here, that B to D or segment BD, it helps us figure this out, but that's not the path that the boat followed. All right, it says point C lies 8 kilometers directly south of point A. Approximate the total distance of the race course. So in other words, we have to find all of the lengths of that triangle. Okay, so we have a problem here, and that problem is we only have 1 degree measurement inside the triangle. Okay, now this is what I mean by a formula a long time ago. What you have is you actually have alternate interior angles, and that just means that if you have two parallel lines next to each other, and then we draw I believe it's called a transversal in the middle there, we can go ahead and we can use alternate interior angles. So if this is 40 degrees here, this is 40 degrees here as well. All right, so once we have that, then we're on our way, and we can use the law of sines. So if one of them is 40 and one of them is 52, that means if we add them together, we get 92. Subtract that from 180, and you would get 88 degrees. Okay, so now we have all the degree measurements inside the triangle. So it's just a matter of using the law of sines to find out what the missing side lengths would be. So I'm going to use sine of 88 over 8, and then that's equal. We'll go ahead and find the side across from the 40 degree first. So we'll go sine of 40. That is over, we'll just call that little side C since it's across from angle C. All right, and then we'll go ahead and we'll figure this out. So I'm going to go ahead and multiply this out here. 8 times sine of 40 divided by sine of 88. Okay, so we got 5 points, and we'll go ahead and we'll go to hundreds again. 5.15. Okay, so the other one, segment BC, kind of the same deal. We'll use sine of 88 over 8. And again, the reason I do that is because I always use the sure one rather than the one I rounded, so I don't get an estimate or a rounded answer to something that's completely off the actual answer. Okay, so let's see. Let's go ahead and go sine of 52, and then over. Let's see. That's little a. There you go. Okay, so again, same kind of deal. Cross multiply here. We got 8 times sine of 52 divided by sine of 88. Okay, so I get 6 points. 3, 1. Okay, so to find the distance around the course, well, all you have to do then is just add all those side lengths. So 5.15 plus 8 plus 6.31. Okay, so 19.46. That would be kilometers. Okay, so that would be the distance of the race. Okay, so last thing, just a classroom discussion here. It says using the law of science. In this section, you have been using the law of science to solve oblique triangles. It says, can the law of science be used with the right triangle? And of course, the answer to that would be yes. You can use the law of science with right triangles. It's just there's probably a lot easier methods than going through the hassle of the law of science. It says, if so, write a short paragraph explaining how to use the law of science to solve each triangle. Is there an easier way to solve these triangles? So we could look into that. We can discuss this in class today. Have a great day.